Okay, so before we move on to kind of new stuff, I wanted to do one more example of this using the Bellman equation and this value iteration idea, applying the Bellman equation many times to solve a problem. I wanted to do one more example, and that's this example, 4.3, which is called the gambler's problem here. So it says a gambler has the opportunity to make bets on an outcome of a sequence of coin flips. So there's two outcomes, either you win or you lose. If the coin comes up heads, you win as many dollars as he staked on the flip. If it's tails, he loses his stake. The game ends when the gambler wins by reaching his goal of $100. So here's his goal state of $100. Or it runs out of money. So here's $0. On each flip, the gambler must decide what portion of his capital to stake in an integer number of dollars. This problem can be formulated as a Markov decision process, and we have some words here. Undiscounted means gamma equals 1. There is no discount factor for the future. It's episodic. That means that it has a definitive end. So it kind of runs until you either hit this 100 state or this 0 state, and then it stops. Okay, so in the rest of the example, they tell you what it is, but we're going to figure out what it is. And we've done, something very similar to this problem before. The state space is all the possible dollar amounts your bank account could be in between 0 and 100. So here you are. Maybe you start here at, say, $50 or whatever you start at. And you can either go up or down depending on what you bet. But the state space, certainly, what is the state you are currently in? It's just what number of dollars you have. So the state space is the, say, S is between 0 and let's call this one the target. And target. I guess we're using S's down. Let's call it N target. That's the number of dollars the person wants. So it's an integer between 0 and N target. Sometimes people do that with two close brackets. And S represents having S dollars. Okay, and the new part, so this is the state space. So far we've seen Markov chains with the state space going between these two things. The new part is the actions. And in this one, the actions are representing what choices you can make. And in this case, I think the actions are how much you want to bet. So how much you want to bet. Between 0 and N target, how much money you want to bet. Those are the possible things. A represents betting A dollars. So when you pick the action A, if A is 3, that means you're betting $3. And so one thing to note, you can't bet more money than you have. So we have this notation A of S. These are the possible things, possible actions that are available at state S. And in this case, the actions that are available at state S are the numbers between 0 and S. Okay, maybe there's a silly way to write out the numbers between 0 and S. Let's write out a simpler way. 0, 1, all the way up to S. Okay, actually it occurs to me, we shouldn't allow the gambler to bet 0, because if we allow them to bet 0, the game might never end. They just choose to bet 0 forever, and then we don't know what to do. That would be bad. So let's do between 1 and S. That's how much money you want to bet. That is the state space. What is the update rule? So the Markov decision process, the update rule, the state at time n is the state at time n minus 1, and then it's plus a coin flip. I'm going to do a coin flips with these Greek letters Cn. So Cn is either plus 1 or minus 1 with probability 1/2 or probability 1/2 if they're coin flips. And the gambler is betting A. So the action they chose, A n minus 1, goes here. So that multiplies the coin flip to decide how much they move up or down. And I will say it's actually more exciting. It turns out if you make it 50-50, nothing interesting happens. But if you make it an unfair coin, so we're going to make it P and 1 minus P, where P is the probability of heads on the coin, then it's a little more exciting. So this is the Markov decision process. It's fully described by this rule. You choose the action A, how much you want to bet, and then you go up or down depending on the outcome of a coin flip. And the question is, what is the optimal strategy and how do you solve for the optimal strategy. And we're going to do it with value iteration. That's what we're going to do. And we're going to compare to what's going on in the textbook. And this is a little bit different. Unlike all the other videos, I have not prepared the code beforehand. So we're going to do like a little live coding and see how embarrassing it is for me as I type this out. So that's what we're going to do. We're going to start with defing and try to get to a solution to this problem. So the first thing we got to do, as always, we got to import our packages. I'm going to do numpy as np. Okay, and you could use JAX. So JAX does all the same things as NumPy, but runs on the GPU, so it's faster. I'm just doing it with NumPy because it's a little easier to do things like with NumPy. Maybe it's not going to run. Okay, with NumPy, you can do things like if m is an array, let's make it the array, I don't know, 1, 0, comma, 0, 1. So in NumPy, you're allowed to do things like m of 0, 1 is 7, and that's okay. And that will update the value of m. But in JAX, you have to do this like .at thing, which is slightly annoying. So I'm going to do NumPy for this problem, just in case this comes up. And then at the end, I'll just convert all the NumPys to JAX NumPys. That's usually how I operate. So, okay, we don't need this, and we don't need this. So what do we need in our problem? What are the parameters in our problem? Let's make a function. And I guess it's a gambler's problem. What are the inputs? There's p heads. That's the probability that the coin is heads or tails. There's n target. That's the target value. You might think we should input the starting value. So like, where do you start? Like I said here, we started at $50. But actually, the solution, as we've seen, involves kind of solving for what's going on everywhere all at once. So I'm not going to input that. We're doing value iteration though, and value iteration has some number of iterations. So let's do iterations, and by default, let's do 10. Okay, and we want to output. We're going to output. At the end of the day, I think the thing we want to output is the value function, v star. That the optimal value function, when you make the optimal choices, v star. And I guess we could have, let's put a star as well. So we want to, can I make this a bit bigger? Yeah, okay, let's try that. Okay. So what is this function doing? Given the gambler's problem, find the optimal value function, v star, and the optimal action, a star. Okay, and this is for any given state. Okay, so what are v star and q star? Well, v star is going to be a function, right? Strictly speaking, v star is a function. V star is a function. It is always a function from the state space to R. It tells you the value of a state if you play optimally, right? V star of some state S is the expected value under optimal play of the total reward you get. The total reward is GOT, given x0 equals S, where S is 0, the notation we're using. And we always think of these functions that depend on vectors, these functions that depend on integers, we think of them as vectors. So equally well, v star is in r to the power n target plus 1, where you think of v star, the ith component is a v star of I. So functions are actually vectors here, and we use that all the time in our programming. So let's see what that would look like for us. V star is going to be a NumPy array, np.array, and it's going to be n target long, n target plus 1. So because it starts at 0, and we want to n target, we do n target plus 1. Okay. Similarly, what is a star? A star is also going to be an array. So this is an array with the optimal values, and a star, similar, same kind of thing. It's going to be an array with the optimal betting size betting size. Okay, so maybe more specifically, the ith component, or I mean, let's say the eths component represents the value at s. Okay, and that's true for both of these. So got some nice comments. Okay, np.array of a number I don't think will work, but np.zeros should work. Zeros, okay. And let's compile this thing. And let's check if it's working. Gambler's problem. 10. P heads could be 0.5 and 10. And we'll just leave the number of iterations, and hopefully this will output 0, 0. Okay, good. So it's all zeros and zeros. Okay, so that's V star and A star. That's what we want. The other thing that, of course, we're going to need, and this is part of the Bellman equation, is the Q star function. So Q star is SA, function of two things, S and A. And it's a function, really, from the state space times the action space to R. And because it depends on two things, you can think of it as a two-dimensional array. And that's exactly what I'm going to use. So Q star, you can think of it, Q star is in R to the power n target plus 1, those are the states, times the action space is also integers up to n target plus 1. So it's like a matrix whose entries represent these values, Q star of SA, the optimal value, what you get at state S if you use action A. Okay, so let's put that in. Q star, and it's going to be n target plus 1 by n target plus 1. Okay. Okay, I think this is good. So this is the value function if you play action A. So let's say Q star of SA is the value if you play action A from state S and then play optimally afterwards. And the eighths entry of Q star represents Q star of SA. So we're mixing up thinking of functions and vectors and matrices in the usual way. Okay. All right. And Bellman's equation is telling us the formula for these things. So what is Bellman's equation? Bellman's equation. So in general, it says that, and you can think of it in multiple ways, but the way I like to think of it is Q star of SA is the expected value starting from the state S and playing action A. What is it the expected value of? Well, it's the rewards you get now, rewards now, plus the future value of the state you're in. The value of the state S1. Okay, and in general, you have a gamma here. In our problem, gamma equals 1, so that goes away, times 1. What are the rewards? Maybe I should have made a bigger deal about this. In this problem, we want to make it to $100. That's the target. So the rewards, and this is worth saying, so you have the state space, the action space, and the next important thing in an MDP are the rewards. And the reward, it's a 0 if you don't win, and it's 1 if you win. And winning means reaching the final state. So you don't get any rewards until the last second. So these are kind of like life points, and you get 1 life point if you win the game. You get 0 life points anywhere else. So there are no rewards. So for us, our 0 is going to be 0 unless you're in the final state. So this is going to be 0 for S less than n target. And it's going to be 1 if S equals n target. Okay, so this is a very simple equation then. It just says Q star of SA is the expected value of V star of S1 given S0 equals S and A0 equals A. But if A0 equals A, that means we are betting A dollars. Bet A dollars. And when you bet A dollars and you're at S dollars to start with, two things can happen. So S1 is going to be either, so if S0 equals S and A0 equals A, we're betting A dollars and we're at S dollars, then S1 is going to be one of two things. It's either S plus A if we win, and it's S minus A. And this happens with probability P, and this one happens with probability 1 minus P. Or maybe I should say P heads. P heads. Okay, so you either go up to S plus A or you go down to S minus A. And that means we can make perfect sense of what this expected value is. So for us, Q star of SA is going to be a V star of S plus A. Sometimes it's S plus A. Sometimes it's S minus A. And we want to do the expected value. That means we have to sum up times the probability. So P heads times this plus 1 minus P heads times this. So this is the Bellman equation, and this is what we're going to implement in our code. And it's quite simple in this case. So let's do it, and let's go back to the code. And I suppose one thing that came up that we haven't put in here yet is V star. I made it all zeros, but actually we know the value of one of them, V star of n target. We said that is 1, right? So the value of being at the state 1, you get the reward, then it's 1. The other ones are unknown, and we don't know what they are. I guess we know V star of 0 equals 0. Let's write this down. Maybe I can make this like an initialize, and a little initialize thing. I could say initialize known values. Okay. N target, S equals N target, and S equals 0. Okay. A star is this. We're trying to figure this out. Q star is this, and the Bellman equation is going to be Q star. Okay, let's see what it says. SA equals, let's just copy down the equation. P heads, that's given in the problem. P heads times V star of S plus A plus 1 minus P heads times V star of S minus A. Okay, and this is the Bellman equation, and value iteration says if you want to find Q star that satisfies this, just apply it over and over again, and it should slowly converge to the correct final answer. And what we're going to do is just loop over all possible states. So we're going to do for S in range, n target. Okay, I guess we don't. So here's the thing: we don't need to do 0, right? We don't need to do 0, and we don't need to do n target. This will perfectly work. So range will start at 0 and end at n target minus 1, and it'll do all the in between states. That's S's, and what are the A's? Well, A can be as small as 1 and as large as S. Okay, but to do S, you got to do S plus 1 because of the way range works in Python. So this is loop through all states. This is loop through all allowed actions. And we're doing the Bellman equation. That's for Q star. The other half of the Bellman equation, this is the side, the part that's always the same, maybe a little more boring. V star of S is the maximum over all A of Q star of SA. I guess this is all A in the allowed actions from S. This part is always the same, no matter what problem you're doing. And so for us, what does that look like? In NumPy, it's going to be something very similar. V star of S. We're going to set it to be, I guess we'll do this once we're done this loop. It's going to be the maximum, np dot maximum. Okay, let me just make sure this element y is maximum of array elements. That's what we want. Okay, you got to be careful because sometimes maximum doesn't mean what you think it means, of q star, and we're doing it along the second axis. So axis equals 1. I guess we want it just like this, s colon, and no axis. So if you do q star of s colon, that will take out the slice at state s of all the actions, and we want the maximum. That's v star. The other thing that we have is we have a star. That's the argmax. That's which one is the best one. So a star of s will be np.argmax. Hopefully that exists as a command. Okay, argmax, yep, of q star of s comma colon. Okay, so now I have this code that works. It loops through. This is value iteration. We've done one iteration. To do more iterations, we should just iterate a bunch of times. For iterations in num iters. And we'll just do the whole thing. Okay. That's the code. That's the code. Okay, let's see if it works. Does it do something? So, okay, there's some kind of bug. Let me pause for a sec while I sort out the bug, and I'll tell you what it is. Okay, I'm back. Very silly bug. I said for iterations in num iterations. Of course, num iterations not a list. I meant a range of num iterations. And of course, like I said, loops are not always the fastest way to do things, but to get something that works to start is good, and then you can fix it up and make it faster afterwards. So let's see how this goes. All right, invalid number of arguments. Okay, so np.argmax or np.maximum doesn't like me. Okay, let me pause it again. I'll try to figure out these bugs. Okay, I'm back, and it was remember I said, is maximum the one that you want? And maximum is not the one that you want. This compares, np.maximum compares two different arrays. That is not what I want. I want, of one array, give me the maximum element. And that's not maximum, that's np.max. So np.max I think is what I want. Let me try it now and see what the bug is now. All right. Okay, this is good. So index 11 is out of bounds for axis 0 with size 11. That means that in my s plus a, s minus a thing, I am off by 1 or something like that. So you are not allowed to go over the maximum size, and somehow I have allowed that to happen. And so let me think about how to fix this for a second. Okay, it's so what's going on here is we're reaching states that are larger than what is allowed. We are reaching states that are larger than end target. Okay, so how could this happen? Well, when you bet, and I said you go up from s to s plus a, and I said, the allowed actions are anything starting at 0 all the way up to what you currently are at. So that means in a certain turn, you could double your money. But doubling your money might exceed end target. So s plus a could be that s plus a is greater than end target. So sort of by doing this thing of only allowing bets up to your bank account size, so s minus a is definitely going to always be greater than or equal to 0. So that's fine. This s minus a can never be too small. But s plus a, I made no restriction, and this is a problem because if you bet money and you win, you could go above what is allowed. So there's two ways I could fix this. I could increase the state space. Like I could say, let's make the state space actually include $101, $102, and so on. And I guess the maximum I would need is all the way up to $200 if you sort of were at $100 already. Or I guess, okay, up to doubling your money at 99 would put you at 198. So I would need to include up to 198 in case you were at 99 and doubled your money. That's one way to do it. Another way to do it, just like I restricted, I said you're only allowed to bet up to your bank account size. why don't I make another restriction on the allowed actions and say that you can only bet up to a bet that would take you up to 100. So I said the actions, before I said it's all the numbers, you could bet $1 all the way up to S dollars. But now I'm going to modify that, because if you bet all the way up to S dollars, you could exceed the maximum amount. So I'm going to say the maximum you can bet is either S, or it's the 100 minus S, N target minus S. N target minus S, right? So if you bet any more than N target minus S, you could exceed N target, and we don't want that to happen. So the maximum is either S or N target minus S. Which is it? It's whichever is smaller. So the minimum of these two. You can never exceed a bet that is, you can't exceed S and you can't exceed N target minus S. So those are your maximum bet. So I'm just going to put this in as the allowed actions in my program now. So instead of saying A in range S plus 1, I'm going to say max bet equals minimum. Okay, and this really is a minimum. Like this is like a math.minimum. Math, I don't have a math. Okay, let's do np.minimum. Okay, now it's the minimum, which is the minimum of two numbers. What are the two numbers? They're S and N target minus S. So that's your maximum bet size, depending on S, the state S, and we're going to do for A in range 1 to max bet, including max bet, so I'm going to put a +1. Okay, and then hopefully this will solve the thing. And I guess, okay, one thing, maybe I should put a comment here. The array Q star is going to have actions that never got updated. So be careful. Q star of SA only makes sense if A is less than the maximum bet at S. Max bet of S is the minimum of S and N target minus S. You can never bet more than you have, and you can never bet more than what it would take to get you to the target. Okay, so hopefully it'll work. Let's see. This is fun of live coding. Okay, so it outputted something, and it outputted some interesting bet sizes. So let's see what these look like. I'm gonna plot them as using matplotlib, and the best way to do that is my code. I never ever code matplotlib stuff by hand. You always gotta copy and paste something. So I'm gonna pause the video. I'm gonna copy in some code that plots these arrays as graphs, and then I'll be right back. Okay, so I'm back. This is the code from week 1A, very first class, and I'm copying this stuff on how to plot. So what I'm gonna do, I'm going to make a new function called plot. Instead of plotting a simple random walk, that's what we were doing in week 1, we are plotting the value function and actions, and we're gonna input in V star and A star, and we're gonna plot it. So purpose, plot. V star and A star for the gambler's problem. Okay. I think the input is pretty clear. Output plot. Okay. Okay. So all this figure stuff we want. The title is value function, and the X label is state in dollars. So this is like the S value, and the Y label is going to be the value, and the value is going to be essentially the probability to win. Okay. All right. Okay, this is setting the maximum minimum. Let's now put that in, and we'll have the computer decide. Okay. I guess we don't need to print this. We don't need to print this. Okay, and we'll plot. We're gonna just plot V star and A star, like this. And I think that should work. Okay, let's give it a go. Def plot, value function, and actions. Okay, so what I really want to do, V star, A star is this, and I want to plot them. Actually, let me put it in here. I'm going to plot them as we go. So every iteration I can plot them, and then we will see how they are updating as we go, which is what we want to see. So I'm going to print the iteration, and I can print something like iteration number, and then I could plot the value function of V star and A star. Of course, it's going to start out as garbage from our initialization, but as we iterate, it should get better and better. Okay, so let's see how that works. So now if I call it, it should just print out a bunch of plots for me as we go. Let's see. Iteration is not defined. Iteration. Okay, iteration in the number of iterations. Plot is not defined. Okay, yeah, we gotta import the right thing. Tell it what plot is. Plot means this. Plot means this. Okay. Okay. So it's plotting something. It's not plotting what I want. I wanted a graph with two things on it. This is more than two things. So something has gone not quite right. I'm going to pause it and try to figure this out. Okay, so I think I found the bug here. I put V star and A star in a list and I said to plot it. And I think that the program is interpreting that as like take everything in V star and A star and put them in a big list. So what I really want to do is plot V star, and then I want to plot A star separately afterwards. So I think I want to do something like this, A star, and I guess can I do color? Is that a thing? Let's make the color equals. I don't know if it's gonna let me. Let's not try it. Okay, let's try this and see what it does. So now I should get two plots, and one of them should be the value function, and one of them should be the optimal choice. Okay. All right, we're getting two things. The blue line seems to be between 0 and 1, which is good. The blue line is between 0 and 1. So this is on initialization. The blue line is the value function, and the orange line is the optimal choice, the optimal bet size. So I guess, okay, I'm plotting two things on one axis. Is that what I want to do here? Let me make it, I'm just going to do some copy and pasting and make it plot two things. I don't think it makes sense to overplot these on top of each other. So let me fix that up. Okay, so what I've done, I'm not 100% sure this works, but what I've done is I've copied and pasted this thing, and I've made a figure 2 axis 2. And instead of the value function, this one is the optimal bet. So what is the optimal amount you should bet? Again, the x-axis is still the state, but the y is not the value or the probability to win. The y-axis is the size of the bet, size of the optimal bet. Okay, and now we're plotting A star. We plot it on axis 2. So hopefully this does what I want. Well, let's find out. Okay. All right, so we are getting two plots. I'm going to make them different colors just so we can think, and I think I can use this color equals thing. So why don't we make the optimal bets color equals red, and the other one I think will just stay blue. So color equals blue. It's nice to put it in so you know what's going on. But now I think this is going to do what I want. Let's plot it. So every iteration, and I guess okay, this is not quite working the way I want. It's telling me all the iterations and then it's plotting these things. So why don't I just put the iteration number in the thing here? We'll put it into the text. I will put text. So let's put in iteration number. Iteration, whatever it is. Value function at iteration whatever it is. Okay, and we're going to input in this iteration number. Okay, so hopefully this does what I want. I need to go in here and say, when you plot it, also tell me the iteration. And I don't need this print statement anymore. So let's, hopefully it'll work. Oh God. Okay, give me 1 second to fix this. Okay, I'm back, and the secret command that I absolutely needed and did not put there was plot.show. And what that says is, please plot everything now. If you don't put plot.show, it'll wait until later, and it'll plot everything at the end. And so that's what was going on. I was printing out, we're on iteration number whatever, and then at the end it printed everything out. So if you do plot.show in the command, so when you make a function that plots things, at the end it should plot it, then it works better. So then you can just go back to the totally same thing to print out the iteration number in the loop, iteration number, and the iteration, and then you can plot everything. I got rid of this other input that it had, and now it totally works. So let's rerun everything and see what is going on. So, okay, so let's look at these. Look at the input. So at iteration 0, this is initialization. The value function goes between 0 and 1. I added in these dotted lines at 0 and 1 so we could see how it's going between them. It starts out as 0 everywhere except for it's a 1 at the target, which is 10 here. The optimal bet starts out as all zeros. It's some garbage guess. So this is iteration 0. We haven't done anything yet. Iteration 1 is what happens after you run the thing once. Okay, maybe try to see a little bit more here. Okay, this is better. Okay, so iteration 1, we've run it once. And you can see the value function is now somewhere between 0 and 1. So the value has increased. So for example, at state 5, the value it thinks is 0.5. And that makes sense because at state 5, you can bet all your money, go all in. If you win the bet, then you win half the time. You win, half the time you lose. So at least you should win half the time at state 5. And look, it found out that the optimal bet size, it thinks it's 5 at state 5. That's going all in. Okay, so that's looking good. And if you keep going, you see that after a few iterations, the value function is this perfectly straight line. And this makes perfect sense with what we discovered earlier. We found the analytical solution to this sort of fair, when the probability of the coin is 0.5, this fair gambler's problem. The value function is a straight line between 0 and 1. And because it's a straight line, no matter what you bet, you're always going to be getting the same value. So there's nothing going on here. In this fair gambler's problem, the value function is a straight line between 0 and 1, and it doesn't matter what you bet. So the optimal bets, it's going to find something because the argmax function is going to find something, but there's more than one solution. All the solutions work. So kind of boring, kind of nice picture that I found. I don't know why it found this particular configuration, but it seems to be working. So the exciting thing in the gambler's problem that makes it really non-trivial is what happens if it's an unfair coin. And we can see what happens if it is a coin in your favor. So if it's a coin that's good for you, let's see what happens. And let's make this 0.75. So you win this coin flip 3/4 of the time. And to make things a little more interesting, let's make the state space a little bigger as well. Let's see what happens now. Okay. Ooh, interesting. Not what I expected. Okay, let me scroll up to the top. Okay, I need to scroll this here, and then this scrolls here. Okay. So it starts out the same way. And the first few, it takes a while for it to figure out what's going on. But over time, you find this value function where the optimal bet size looks like it's stabilizing around 4. 4. Okay, that's interesting. So the optimal bet size is always around 4. 3. Okay, here the optimal bet size has gone down to 3. Now it's gone down to 3. I think if we keep running it, it should find the optimal. I'm guessing the optimal bet size is 1. When the coin is favorable for you, you want to make as many tiny little bets as you can. The more bets you do, the more your chance to accumulate luck happens. So we've done some number of iterations, and it's found that the optimal bet size, it thought it was like 4, and then it went down to 3. So I wonder if I run even more iterations. So that was 10 iterations. Let's run 50 iterations. And I guess let me make it only plot every 10 or something. If iteration divided by 10 is 0, then plot everything for me. Otherwise, don't plot everything for me. So we'll only see every 10 iterations. Okay. So what's going on here? Okay, spoiler. We wanna. Yeah. Okay. Here. Start at the beginning. Okay. So we start with nothing. Great. Iterations 1 to 10 happen. The value function is looking like this. Optimal bet size, it thinks it's a 3. 20 more iterations happen. And what has happened, the optimal bets have gone down to 2. So it took the computer a while. It had to do a lot of iterations to get down to this bet sizes of 1 and 2. Then we did 10 more iterations. And now the bet size, okay, it's still 2 in the middle. But a lot of places have an optimal bet size of 1. Did more iterations. And now it has figured out that the optimal bet size, you make a bet of 1 everywhere you go. Okay, and it found out this optimal thing. So the optimal bet size is always 1, and you have a pretty good, unless you get really unlucky, you're gonna win the game. Just always bet 1, make lots of small bets. So that's cool. I think it's cool seeing that the value iteration takes a while to figure this out, even though it makes logical sense. The really exciting thing is what happens for coins that are biased against you. This is like an actual casino, right? It has like games that are not 50-50, but are like 40% to win. So if you have a 40% coin, what does it look like? And this is going to be something cool. Okay, so let's scroll down to the bottom. So first of all, you can see the shape of the value function is below a straight line, right? So a straight line is a fair coin. If the coin is rigged against you, you have less value than a straight coin, right? You're less likely to win than a coin that would be fair. So it starts to look like this thing, and the bet sizes have a weird structure where sometimes in the middle they're quite big. Like at state 15, you should go all in, bet all your money, and so on. And I think this hasn't settled down yet. This still seems pretty crazy to me. So I think I'm going to run even more iterations. Let me not print these out. Let me print them out only at the end. So let me just run all the iterations and print out the final thing. Okay, so we ran all the iterations. We got this. Okay, that's 50. Let me do like 200. How long will that take? Let's do 200 iterations. Okay. All right, so I guess it's settling down on this, which is some crazy thing, where it thinks you should go all in at 15. You bet a small amount when you're close to losing, and you kind of have this weird back and forth in between. I don't actually know if this is the right answer or if we need more iterations. I will show you guys what is done in the textbook. So this kind of thing is exactly what the textbook is trying to show us. So here is the textbook that this problem came from. Example 4.3, the gambler's problem. Okay, they did 100, and they did a coin, so they let p heads denote the coin, and figure 4 shows it with p heads equals 0.4 and 100. Let's do 100. So here I was doing 30. Let me do 100 as the final state instead of 30 and see what happens. Okay. A little better. Okay. And now we have the same kind of picture as the textbook, where we have this kind of like structure where it goes up and down and up and down. It makes sense. We should get the same answer as the textbook. So here is what they settled on, what's going on is the optimal bet is going up and down and up and down, and you have these all-in points. So at 50, you go all in and hope to win. At 75, you bet 25 and hope to go all in. At 25, you also go all in to try to get to 50. So you have these points 25, 50, and 75. And they didn't tell me how many times they ran it. So I don't know if I've run it enough times to get to this optimum. So I have something pretty similar. This peak at 25 and 50, but I have these other peaks as well. I wonder if I run it longer, if it will go away. Let's run some more iterations and see. So let's see. I guess probably most of the time is spent printing out this stupid thing. Let's print out only every 10th iteration. Okay, so here's what it thinks it looks like after many iterations. Okay, and I could tell you if maybe this could be equivalent. Like the optimal bet size, there could be more than one optimal answer. So the way to really check if I have the same thing as a textbook would be compare this function. There should only be one value function. And does that look? I mean, it looks similar to what they have. And they're showing you how it's kind of creeping up as you run it. That was what we were plotting at first. Okay, so that is an example of value iteration from the textbook, example 4.3. Hopefully done in a little more hands-on way than what I did with Pig. Okay, I'm gonna stop there.